Good morning students. I, Dr.S.Pethanachi Selvam, Head and Associate Professor, the Standard 5 Works Rajaratnam College for Women, Sivakasi. This session we are going to see Introduction to Complex Analysis. Here the objective, what's the purpose we are learning? The objective is to know the concept of complex number system and its geometrical representations, and what are its applications, and then what are its general properties of complex number system. Why complex numbers necessary? Complex analysis is one branch of mathematics. It was developed to enrich complex valued functions, their properties and the properties of analytic functions. Where it is applied, complex numbers are used in engineering field and scientific field, including electrical engineering. It's also used to define wave functions and predict particles' behavior at the quantum level. Also, it is used to represent periodic functions like waves, alternating current and light waves. It's also used in Fourier analysis to break down the signal into its components. How the complex number system is developed? Why it is written as A plus IB? The collection of all complex number systems are derived from real number system. If you have a quadratic equation ax squared plus bx plus c equal to 0, we all know that it has two real roots. If the discriminant value b squared minus 4ac is less than 0, here we can't find the real root. To overcome this problem, the imaginary unit was introduced. Its value to be equal to I squared equal to minus 1. Using this notation, the solution of the quadratic equation x squared plus 1 equal to 0 are I and minus I. Now we have the basic definition of arithmetic of complex numbers. Usually complex number system denoted by C, and it is the set of all ordered pairs of real numbers with usual operations and addition and multiplication, which are defined as follows. That is AB plus BD, CD equal to A plus B, C, B plus D. And AB into CD can be written in the form AC minus BD and also BC plus AD. And also the next one, we can check the operations, multiplication and addition. What is the identity element? What is the inverse element of ordered pair of real numbers? 0, 0 is the additive identity. Minus A minus B is the additive inverse of A, B. And also multiplicative identity in this set is 1, 0. And multiplicative inverse of the ordered pair of non-zero element can be calculated by using another element alpha, beta. Apply the multiplication definition, you can find out the inverse elements alpha and beta. Therefore, the set form that is the field, that is under addition and multiplication satisfy all the conditions of a field. Therefore, the set of all ordered pairs of real numbers form a field. If you consider a set S, it consists of ordered pair of elements of the form A, 0 and A belongs to R. Clearly, it is a subset of C. We can prove that the set S is isomorphic to R such that the complex number A, 0 corresponds to the number A. That is a real part. That is, we can write A0, the complex number, as simply A. When you apply A is multiplied by A, 0 is a complex number. Another complex number C, D. We multiply one more number. As usual, every complex number can be written in the form AB can be written as A0 plus 0B. Therefore, we can get the number A, B. And it can be written in the form A into 1, 0 plus B into 0, 1. Put 1, 0 equal to the root of minus 1. That is 0, 1 equal to I. Thus, a comma b ordered pair can be represented in the form a plus ib, where I squared equal to minus 1, that value equal to ordered pair minus 1 comma 0. Therefore, the real and imaginary part of a complex number a plus ib can be denoted as real and imaginary. Then a complex number is denoted as z equal to a plus ib, where real z equal to a and imaginary z equal to b. Here these are the basic properties of complex numbers. If you have any two complex numbers, when do you say that two complex numbers are equal? Their corresponding real and imaginary parts are equal. That is z1 equal to z2, we can say that if and only if a1 equal to a2 and b1 equal to b2. Similarly, the arithmetic operations addition, multiplication and subtraction and also division can be manipulated among complex numbers. z1, z2 can be added, that is real parts to be added, separately imaginary parts to be added. And as usual, subtraction also can be done in the same way, and multiplication, by using multiplication we can define, and in addition your complex number z2 not equal to 0. Then similarly come to the next definition, complex conjugate of a complex number. It is denoted as a minus ib. What are its properties? z1 plus z2 the whole bar, as usual the difference conjugate and multiplication conjugate and also the division conjugate, as well as z double bar equal to z, and also z plus z bar equal to 2 into real z, and z minus z bar equal to 2 into I into imaginary z. The matrix of the modulus of a complex number denoted by root of, suppose your complex number is a1 plus ib1, the complex number is root of a1 square plus b1 square. Now next one, these are the basic properties, and how can we represent in geometrical representation, how can we represent a complex number in the xy plane? Here we can see that in picture, it has 2 points z in the xy plane, a comma b, and z bar, the conjugate, that is in the fourth quadrant, a comma minus b, it is just the reflection, and here the modulus value of the complex number a comma b. The length of a modulus of a complex number is mod z, and it denotes the length of the value is equal to mod z, having values equal to root of, it's a distance between the points origin 0 and the point z, and its value equal to distance between 2 points 0 minus a the whole square plus 0 minus b the whole square. Therefore, the modulus or length of the vector oz, that is a vector, that is oz bar equal to modulus of oz bar equal to root of the distance between the points, that is a square plus b square. It represents the length called as the modulus of a complex number. As usual, the properties of modulus, here already we have seen the operations how it plays, and here also the properties of modulus z bar and z1 z2, mod z1 into z2 equal to mod z1 into z2, and also the triangle property mod z1 plus z2 less than or equal to mod z1 plus mod z2. Here this property triangle inequality can be extended to n complex numbers, that is mod z1 plus etc mod zn less than or equal to mod z1 plus mod z2 plus etc mod zn. When we go for polar form of complex numbers, if you take any point P, it's in the plane, in the xy plane, then, and here you represent the modulus, it is denoted as r, OP, the vector OP, and he can resolve the vector OP along x-axis and along y-axis, then we can get the angle of inclination theta along the polar, along the initial line, then polar line OX, then it will, when you resolve the vector OP along the real axis, we can get the coordinate r cos theta. When you resolve along the y-axis, that is the imaginary axis, you can get the value r sin theta. Therefore, the point will have two coordinates, so one is r cos theta, another one is r sin theta. You complete the triangle, then r value you can get it as usual modulus. And what is the angle cos theta? Opposite side by hypotenuse. Opposite side value equal to, that is the distance x comma y be our complex number, the distance will be equal to opposite side. The cos theta value equal to adjacent side x by r, and sin theta equal to y by r. Therefore the point, the complex number x having coordinates r cos theta and y equal to r sin theta. Therefore our complex number will become x comma y will become r cos theta and r sin theta. Therefore we converted the complex number into polar form. Here you have a complex number 1 plus I. We can express it in the polar form. That means first we find out r and next we find out theta. Then only we can write cos theta and sin theta. Here the modulus value equal to x equal to the real part x equal to 1 and imaginary part y also equal to 1. Therefore the length of the complex number, the length of the vector equal to modulus z, which is equal to root of 1 plus 1, which is equal to root 2, and theta equal to argument of the complex number, and then its value equal to, that is tan theta equal to y by x. Therefore theta equal to tan inverse of y by x. Put the values of x and y, imaginary value 1 and real value equal to 1. Therefore tan inverse of 1, that value equal to pi by 4. Then your angle cos theta equal to 1 by root 2 and sin theta also equal to 1 by root 2. So therefore we can express the complex number 1 plus I in the form r cos theta, that is root 2 cos 45 degree plus I into root 2 sin 45 degree, and then the complex number 1 plus I expressed in the polar form. And next one is very important concept is principal argument. Here theta equal to small a of argument of theta, and here that always the argument value theta lie between angle minus pi to less than or equal to plus pi, whereas the principal value of the argument is denoted by of a complex number is capital R z, and its bound varies from minus pi to plus pi. And here always another formula, argument of, that is argument of z1 z2 equal to argument z1 plus argument z2, argument of z1 by z2 equal to argument of z1 minus argument of z2. How can we find the integral power of any complex number? That is given as you express the two complex numbers in polar form, and suppose multiply the two complex numbers, then you can get it r1 r2 into cos of theta 1, apply the formula a minus b, a plus b formula, then r1 into r2, you can get the result. Put z1 equal to z2 and apply the result, then mod z squared equal to mod z the whole square. In general we can extend this power to up to n, therefore mod z power n equal to mod z the whole power n, and here theta is the argument of z and n theta is the argument of mod z power n. Then the next one is problem related to this argument. Suppose you find the power, integral power of the fourth power of a complex number root 3 minus I. Here also you find the modulus, here a equal to root 3 and b equal to minus 1. Find the modulus of this complex number z, its value equal to r, and find out sin theta and cos theta and find the angle theta, and then express the power, that is z squared, that is r power n into the value. You can express it, then you can find all the powers. Here example I am taking the power of integral power of z power 4. And then the next important definition is what is meant by a finite complex plane and extended complex plane. All complex numbers except the number infinity are called complex numbers, and the complex plane containing only the finite complex numbers is called as a finite complex plane, whereas the complex plane containing complex numbers together with the infinity called as extended complex plane. And here using this definition we can define an important projection, that is we have to find an one-to-one correspondence between the unit sphere and the extended complex plane, and you take a complex plane by, that is p, that is a point, any point on the complex plane pi, and you split the coordinate and then you draw the unit sphere. We have to find an one-to-one correspondence between the points of the surface of the sphere and the points of the extended complex plane. Take the extended complex plane by pi and the coordinate axis, you take the z axis, you take the point then the point is n. On z-axis, the point having coordinates 0, 0, 1. And then you have to take any point P on the plane, then you can correspondingly point P dash on the surface of the sphere. Therefore, you draw the line, therefore there is an one-to-one correspondence between each point of the sphere and also on the plane, the surface of the sphere and also the points on the plane. If a point at infinity corresponds to n, then there is also one-to-one correspondence between the points of the sphere and the points of the extended complex plane. This correspondence is called as a stereographic projection, and the unit sphere is called as the Riemann sphere because we have taken the sphere in three-dimensional space. Now we have found the one-to-one correspondence between the points on the complex extended plane and also the points of the sphere. This sphere is called as a Riemann sphere. Thank you all. Thank you.